to get in some different, I'm going to start changing things. It looks like a few people aren't here yet, that there, but I'm going to go ahead and get started anyway, that there. Okay. As I look at the Floyd book, or the book that there, let's see if it picks up the same book here. And actually, I want to go to page 386. Nope. Okay. All right. I'm going to switch books here a little bit, just simply to cover a few things here. There. Let me just kind of jump in here where we're at, and then move on to the next subject. Here is we talked about the SR flip flop, right there, and you have the NAND gate that looks like this right here, where you take the input. Yeah, and I'm not drawing it right. You know, I'm going to cheat. Might as well just cheat a little bit here, and right here, just kind of quick review. Oh. Right there. These are the two basic SR flip-flops, and as we recall, you should remember that whenever the set goes there, Q is going to go high, and Q naught will go low. Whenever the reset is pulsed, the Q goes low, and the Q naught goes high. At there, whenever they're both low, the output doesn't change. And the input of 1-1 is not allowed. Right there. That's the SR flip-flop. Right there. The next flip-flop we talked about, and I'm just going to kind of jump through there instead of redrawing them each time. Right there. Right there is, this is the truth table for it. This shows kind of an example of how that worked. I'm not going to go through it again. We spent enough time talking about it. That there. There. This shows a typical 774-279 quad SR flip-flop. Now notice that this particular flip-flop uses active low inputs, which is very common for that there. So when I say that S is active, if we're using this particular one, that means it goes low. It's pulsing low for an active low flip-flop. That's there. So, and they call this a latch. Sometimes you'll use the term flip-flop and latch interchangeably. To me, they mean something different. Usually, when I think flip-flop, I'm thinking of something that is clocked. So, that's there. But this is that there. Notice that each of them has two S inputs in this particular case right there. They both have to go active in order for it for the output to be set. So in other words, if you look at this particular flip-flop, you see that we use the NAND gate here, right there, but it's a 3-input NAND gate. So the commercial SR flip-flop in this particular case requires that we have 2 of those. One of those is usually used as a enable pin to enable that there. If you want to use it as a normal, you just tie the 2 of them together, right there. You just tie the 2 inputs together. It operates as a normal SR flip-flop. The next one we talked a little bit about was the D. We talked about, the gated. Again, in this particular case, the gated simply has the enable that goes to that there. And if you look at the one we just showed, actually that extra input is actually the enabled, that there. So at there. So again, we look at the enabled right there, that's the gated. And then we have the edge triggered. We talked a little bit about the edge trigger. And when we see a clock signal going in, and again, we're looking for this triangle. That triangle means that it's edge triggered right there. So if you see it like this and there's no bubble, that means it's a leading edge trigger. If there's a bubble, as in here, this is a falling edge or trailing edge trigger. So that trigger means that we only look at S during the rising or falling clock edge, or R. We only look at the inputs that there. The other one that we talked a little bit about was the D flip-flop. The D flip-flop basically is an SR flip-flop with only one input, but we take the input on the S and we run through an inverter, and that goes to the R. The D flip-flop is a very commonly used one for latching data. That's there. An example of that would be, for example, in the microprocessor world, right here, we have coming out of the microprocessor a series of lines called AD0 through AD7, for example. This is for the 8086 that's there. And what this basically says is that some of the time it's an address line, and some of the time it's part of the data bus. And when we wire up our microprocessor system, we take these lines through here. They go through something called an address latch right there. And what this address latch is an 8D flip-flop, or actually that's there. And we have a line coming out of our microprocessor called the address latch enable. And what the processor does is it places onto the bus a valid address. And my handwriting is bad because I've got to put there. While the address is valid, it takes the address latch enable high. At this point, that tells this device to latch in the address, and then it now becomes the data bus. So these latches are very, very important as we design microprocessor systems right there. Other places where they're very important is when we want to grab the data at a particular point in time. So all we're doing with an address, with a latch, either gated or using a clock, is we're controlling when we latch that data. Because once we latch this data at this point, it's no longer an address bus. The microprocessor is free to change that data to wherever it wants, and then the memory, the address lines are still the address lines. And then we can use the same lines out of the microprocessor for moving data in and out, right there. And the reason we do that is to save real estate on the board and real estate on the microprocessor as far as the number of pins. That there, we share the lines. They're multiplex. Some of the time they're address lines. Some of the time they're data lines. That's used in a lot of different applications. This is the simplest one right there. So we use the D latches for that. They're not necessarily called D latches when we look at an address latch. They're just called an address latch. But what's internal is 8 D latches. That's there, and they're D latches and they're gated. In the case of an address encoder, they're usually not clocked, right there. But at this point, this tells it to latch the data, and this tells it to just hold the data, right there. And then the data is free to change however it wants on the lines that there. So we got there, because when we look at a microprocessor system, we've got memory over here, and the memory has going into it some data lines, and it has some address lines. They have to be separate, right there. Coming out of the microprocessor, we've got one set of lines right there. We run these through the address latch, right there. along with the ALE, the address latch enable, right there. So these 8 lines go to here, and the same 8 lines go to here, right there. So we've got the same lines coming out of the microprocessor, but we separate them out using our D latch right there, our series of D latches. So it's a very commonly used type of flip-flop or gate for that there. So that there's, and go back. You know, I'm scanning the book instead of using the slides simply because I discovered slides are missing too much. And welcome, folks. I didn't lock the door today. During lectures, I don't lock the doors. It's only during labs that I lock the doors. And I actually warned the other class, you know, the non-transfer degree class is running for the September. I warned them already that on lab days when we meet in the labs, beware. After 15 minutes, the doors get locked. That's there. That's there. I ran into some interesting comments when I do that there. So again, we've also got the JK flip-flop, which the book here kind of goes through this here. And I did make available the Floyd book. You have that, right? You should have 2 books in your collection of books. One is Floyd. That's the one I'm talking about today. The other one is Tochi. Just kind of a reminder. The Floyd book is a more detailed book. It has much more detailed. The Tochi is easier to read. So keep in mind that I will use exam questions, and when I do the review for the final exam, I will point out that some of the questions will come out of Floyd, some will be coming out of the Tochi book. So they cover the same materials, and the chapters are almost the same. What I recommend that you do is that you read the Tochi book first, and then you read the Floyd book. The Tochi book is easier to read, but the Floyd goes into more detail and but it's an easier book to do. Okay, this actually shows, again, the D flip-flop, the internal organization. Don't be surprised if you see a question that says, how do you make a D flip-flop out of a JK flip-flop? How do you make a D flip-flop out of an SR flip-flop? I would expect you to know not necessarily the NAND gate structure or the NOR gate structure, but how these flip-flops are related to each other and the truth tables for the flip-flops. That's it. So, again, this is the D flip-flop. I talked about that there. And again, basically they have inside the flip-flop this transition detector, and all that simply does is it changes our clock to a series of impulse functions. Very short glitches is what they're going to look like right there. Okay, the next flip-flop that we talked about, and I'm reviewing these because a lot of questions come on in flip-flops. That's why I cover some material twice. I'm deliberately covering it again. That's there. Is that the JK flip-flop is the most commonly found flip-flop out there. And it's not used necessarily so much for latches, but it's used for building finite state machines. It's used for building counters. It's used for many, many things in the sequential logic world. So the JK flip-flop, basically, when you look at it right there, and let me just kind of go through again. Sorry, wrong one here. When we look at the JK flip-flop, it has 2 inputs right there, J and K. We also have a clock input there. We have a Q out and a Q not. Later on, we'll see reasons why they definitely have the Q and Q not. Because as we build some of our circuits with these, quite often we want the Q not or the Q, depending on our circuit there. That's there. And our truth table for that is J, K, and then what we're going to show here is at the next clock cycle what the output's going to be, right there. When J and K are both 0, there's no change, right there. The output doesn't change. When J is low and K is high, the output goes low, right there. Right there. When J is high and K is low, there, the output goes high. So those 2 act as the SR in the SR flip-flop. The difference is when J and K are both 1, we toggle the output right there. Right there. We toggle the output. Right there. And that has a lot of very powerful tools right there. So, for example, if I want to build a very simple counter, this is not necessarily a good counter to use, but that's there. But if we look at our timing pattern, if we feed a clock into J and K, that's there, and we look at its output, what we're going to find is that as we do that, we take, our circuit's going to look like this, and I'll do it, record this in a minute. We tie J and K both to VCC right there. We bring a clock in here, right there, and our clock looks like this. Right there, there's our incoming clock, right there. And we're going to assume that it's low to start with. When we hit the rising clock edge, the output changes, right? It stays high, and then it changes again here. It changes high, it changes here, it changes here, it changes here, it changes here. Notice that what I've done is I've cut my frequency in half. Right there. Now if I take the Q out and put that through another JK flip-flop into the clock, again tying V and C high, right, JK high, this one's going to change again like this right here. We throw a third one, it's going to change like this. And we throw a fourth one like that there. So we can get a relatively simple counter that will count down. Right there. So again, so if I break up Quartus and I build this circuit, if I can find Quartus, there's my Quartus right there. And I'm going to go ahead and look at a relatively simple counter that we're going to make using 4 JK flip-flops right there. And create a new project. And I'm going to go through the steps right here. And I'm going to create a new, go through all the steps here. And I'm going to call this JK counter. Now, we're going to be making some changes to it as we go along here, but here, right there, file name, there, and JK counter, right there. And unfortunately, I hate to do this. I have to unplug this so I can hit the finish button. Right there. Fortunately, in the other rooms, you don't have to do that, you know, those screens, but these projectors, I don't know what the resolution is on these projectors. It's something fairly dated that they're. So I'm just going to go ahead and do this circuit here. And I'm going to do a block right there. And again, JK. And it should have just JK flip-flop. Yeah, there we go. Now, as you look at our various flip-flops here, you'll see that we've got a number of them to pick from here. We got one with an enable. We've got the regular one. We don't have one that's got the inverting clock. I'll take care of that by putting inverters on all those. I'm just going to use a standard JK flip-flop right there. Now, when we look at this circuit, let me talk a little bit about this circuit. You'll notice that there's 2 inputs to each one of those, and they're called preset and clear knobs. Those are asynchronous inputs. So those will change the output immediately, right there. So for right now, we're not going to use those. We're going to tie them all to ground, right there. So you notice that they have bubbles on them, which means that they're active low. I mean, we're going to tie them to VCC. We want them to be tied high. I said ground, but in this particular case they're active low, so we want to tie them high. So if we pulse them low, and I'll do that in my diagram, you'll see that our outputs all go to 0 or to 1 immediately. So I'm just going to go ahead and tie everything to VCC right here. So I'm going to put VCC here, and I'm going to tie pretty much everything to VCC. right here. And I'm going to tie all the JKs to VCC right there. Everything is being tied to VCC. I'm going to tie that to Q. Move that out, give me a little bit of room. That's there. And then we're going to tie all these. And I'm just going to put another VCC there. Okay, this is a relatively simple circuit. I tie all the JKs to VCC. I tie all the asynchronous inputs to VCC. So when I tie JK to VCC, then each output's going to change at every clock cycle. So we're going to bring in a clock right here. Input right there. And I'm sorry, folks, but I'm going to have to make this smaller and move it over a little bit so they have room. Right there. Right there. And now what I'm also going to bring out is I'm going to bring out the 4 Qs. Now, in this particular case, you'll notice that I don't have the Q knots shown. That's there. If I went back and I pulled up a part that's in the book, the part number, it would have the Qs. So I'm bringing the clock in here, and what I'm going to do is I'm going to take the Q from each one of these and tie it to the clock of the next one. Right here. Now this is what's called a ripple counter right here, and because first it's going to change in this one, then this one, and then this one. So the effects that there are some disadvantages to this, and it's not very commonly used because we get a lot of clock skew. When I say clock skew, it means that it takes 4 propagation delays before the last one finally that's there. And if you double click on this, I think you get that's there. Okay, it doesn't give me anything. So now I need to put my 4 outputs there. So I'm going to put the outputs, again, I need to shrink it down in order to have room for my outputs here. Yeah. Oh, wire's not connected. Which one's not connected? Oh, this one here. Thank you. That's all right. You should. When it's that small, it's hard to. Okay. All right. Thank you. Actually, the compiler would give me an error when I tried to compile that there. So, but that saves me from there. So now let me go ahead and I'm going to put 4 outputs in here, and unfortunately. Up there. Let me go ahead and put 4 outputs here. Right there. And then we need 4 outputs for each of the Qs. And I'm going to put them down here. Right there. So I'm just going to tie the output each one of these here. right there. And we're going to probably spend most of the day making changes to the circuit and looking at different things here. And you have to be very careful as you connect these things through. Okay. Let's go ahead and name our pins. This is clock. Right. Oh. Clock O. I guess I could leave it clock O. Clock. Now, as we look at this one here, I'm going to call this Q3, Q2, Q1, Q0. Q0. And let me talk a little bit about this circuit here. Right here. Is that, and this one's also not connected. We didn't catch that one. Okay. Now everything's connected. It looks connected there, right? Hopefully. Okay. This one is going to take my incoming frequency and divide it in half. This one here will take it divided by 4, this by 8, and then by 16, right there. So when we look at this, what we're going to see, this is actually going to end up being a countdown timer when we set this up here. And what I may do here is in a few minutes, I may take the clear and set it there. It should start up automatically there. But let's just go ahead, and I'm going to save this. And let's just, okay, flip-flop right here. Let's go ahead and do the simulation, and let's see what the simulation does, and then kind of go back to the circuit and explain what's happening there, right there. So let's go ahead and do the simulation file. Now this particular simulation file is going to be a little easier than the other because we don't have to end time, and I'm going to set that to 10. It doesn't have to be that high. I'm going to set my grid size to 100 this time, but we're going to blow it out in order to talk about a few things here. Node finder, all list. Oh. Well, you know what? I have to compile it before I can use node finder. Right there. Because until I compile it, it doesn't see the pins. There. And since I didn't bring a board to set this up, I won't worry about assigning pins or anything. Okay. Now this gave me a warning right here. And this is a interesting warning there. You see this comment here. It says found 3 nodes in clock path which may be acting as ripple or gated clocks. So the software knows what I'm doing is a very sloppy design. Right there. We'll see why it's a sloppy design, but it's the easiest way to see how counters work without getting the designing more elaborate counters. And today is just kind of introducing counters, and then after that, finite state machines. We'll get into the proper way to design them later. That there. So once we've done that, we can come back here, and I'm going to close that since I've got there. Let's go ahead and put my pins in, node finder. In this particular case, it found them all right, that there. So we can go ahead and bring them that there. And I'm going to go ahead and group these. Grouping. Group. Right there. And Q out. Yep. Q out. Right there. And I want to make sure it says that the least significant, we got it backwards. I need to ungroup them. Okay, what I was looking for there, let me just kind of point it there. This says most significant bit is on top right there. I'm going to change that to least significant on top. But the main thing is that when you group it, when you do the group, the most significant bit has to be on top when you form the group. Otherwise, it's going to be in the wrong order right there, and it doesn't work properly. So at this particular case, all I'm going to do is I'm just going to tell it to put a clock in. Right there, start to, yep. So our only input to this right here is this clock right there. That's our only input. So we're going to go ahead and save that right there, and then simulate it. And what we're going to see when we run the simulation is garbage. Why is that? That does not look right at all. F. It's got these reversed again. My bits are reversed. That's there. All right. Let's go back and start this over again. Let's ungroup these. Right there. It says most significant is on top. Hold on. You know what the problem is? I got these reversed. This should be, no, that should be Q3, Q2, Q1, Q0. This one should be changing twice as fast right there. Right there. Let me simulate this and see what happens again. That's there. I know that the data is wrong, but Q0 is changing right there because it should go to 7. This should go low. This should go. All right. It's not changing right. The frequencies are doing what they're supposed to be doing. Right there. This should go 7, this should go low. This is still showing the wrong bit order. Right there. I mean, if I ungroup it, it looks right. What's wrong is the grouping. So let's ignore these numbers up here. We're going to ignore those numbers right there. And I'm just, for whatever reason, the software is not being kind to me. And I know that stuff frustrates people at no end. I'm sitting in front of a group of people. I'm not going to try to fix it right here. Let's just look at what's happening on the waveforms. Right there. Let's just ungroup it. And run it again here without the numbers. You normally stay awake. You're having trouble today, aren't you? You keep wanting to doze off. Half there. Nobody likes to be pointed out that they're dozing off in class. There. Okay, let's look at these waveforms. Let's talk about these waveforms a little bit here. That there. Okay, I'm going to explode it out here so we can see what's happening here. Right there. And talk about these waveforms. When we start this discussion right here, notice that they're all low here, right? Everyone sees that they're all low. They're all low right there. And then at this clock edge, this rising clock edge right there, notice that they all went high. So we go from 0 to 15. Right there. They all go high. On the next rising clock edge, right there, Q0 goes low, and Q1, 2, 3 stay high, so we go from F to E. right there. We go to our next clock edge. This one goes high, this one goes low. So we now go from F, or E to D. And as we go through here, we will count, we'll get to the point where they're all 0, right here. Notice that they all end up, finally the last one, right here is Q3. You know what? Yeah. So the bits are going, kind of a funky order right there. What is going on here? This is a standard ripple. Let's go through and look at this again. Make sure I'm at there. They all go high. Then at this point here, it's going to be. I can't write on this right here, but you know what? I didn't bring it with me. So this works fine. Yeah, see, that doesn't work with with this projector. That there. Okay, going back to okay. Let's see if we can follow this through here. This is F, right? This clock edge is 1 1 1 0. That's E. This clock edge here, it goes 1 1 0 0. This one here is 1 1 0 1. Here it's 1. Yeah, okay. 1 1 1 1. This clock edge here it's 1 1 1 0. This clock edge here it's 1 1 0 1. This clock edge here it's 1 0 1 1. Here it's 1 0 1 1. That's right. It's counting down. Here we get to 1. This clock edge here is 1 1 0 1. We're there. 1 1 0 0. Here it's 1 0 1 1. That's right. 1 0 1 0. Here it's 1 0 1. So 700 is where we're at. Right here. 700. And then at 800 we go 1 0 0 0. And then the next one we should go 0 1 1 1. We're at 7 there. Here we're at 7. Here we should go to 6 1 1 0. Yep. Right there. 6. Here is 1 1 here. This one here is 1 0 1. That's 5. And then here we're at 4. 0 1 0 0. So we're at 4. Here we're at 3. Here we're at 2. Here we're at 1. Here we're at 0. And here we go back to F. So it's counting correctly. It's kind of a pain to see it count. And life is much easier when the numbers work with the grouping correctly. That there, but for whatever reason, my grouping does not work right here. And I don't think I can group in here. Grouping, group. Right there. Oh, that's not going to work. It overwrote that there. So I'm going to try the grouping once more and see if we can. Group hexadecimal. That there. That's fine. I'm going to try the group once more. Display count is binary count. Break count. Okay. I'm going to simulate this once more and see what happens, but I think no, but it's still doing its funky thing. It's still got the bits reversed. And the reason I can see it's got reversed because right here, Q0, that should show up as an E, and it's showing up as a 7. Okay, see that? So the software is not being kind. If I go back here and ungroup it, reverse these, group it again, right there, right there, simulate it once more. Sometimes you keep doing it and all of a sudden it starts working. Now it's working right. Okay, don't ask me what I did wrong before. Don't ask me. That's part of the nature of the software. It's frustrating. I did the exact same thing I did the first time, right? And now it works. But as you can see, what we've got is a counter that counts down from F down to 0 and then resets back to F right there. So we've got a ripple counter, and the reason I call it a ripple counter is that if you look at our changes here, and we'll look at this one right here, you can see that's a good one right there. You can see that this one changes. Where's my clock edge? You see, there's where my clock changes. It takes all the way to this time here before the first one changes. And then after the first one changes, this one changes. Then this one's supposed to change, then that one changes. We've got some kind of conditions going on that causes the race. But we're seeing that when we go from 0 to F, we go through 1, 3, and B. We got 3 wrong answers right there. Now, if we want to change, if we look at the next one, only 1 bit changes right there. See, we can go from F to E immediately. Because only 1 bit changes right there. Only 1 bit changes. So typically, I mentioned something called the gray code earlier in the class, where only 1 bit changes at a time. So if we're going to use this type of design, then we would normally want to use a gray code output right there. And when we design these types of counters, that only 1 bit changes, so we don't get these erroneous conditions. The better approach is to have them all tied to the same clock. All I'm trying to get across today is basically what a counter is supposed to do, and how we can use JK flip-flops to design counters. Now, what our ultimate goal is to design these in such a way that we get a counter that we tie all the clocks together, and we have a synchronous counter. This is called an asynchronous counter, where we have multiple clocks. That's there, and that's a bad thing to have happen right there. But we've set up a counter right there, and when we get into the next chapter here, they talk a little bit about counters here. Up there. Let me go back to my simulation here and just kind of point here, or go back to my drawing here, right here, and I'm going to, instead of tying these to all on the clear knot, instead of tying the VCC, I'm going to put an input in there, right there. So let me delete that, delete this here, and I just want to show right here. Let me put another input here. Input here. And I'm going to name it clear knot. And I'm going to tie it to that there. And then go back to my, save that. I just want to show what this recent, that clear knot does, how it works right there. Okay, right there. So now I've added that, and I'm going to move it up to the top. Right there. And then I'm going to set it to high, right there. And then somewhere along here, I'm just going to set it low there. So I'm just pulsing it low for a short period. So now when I simulate it, right there, just notice that I went from D right to 0, so my synchronous clear. And if you also notice that I put my synchronous clear where it went low on a trailing edge instead of a rising edge, it didn't wait for the rising edge for it to go low. So that's a way of resetting the counter midstream right there. If I would, right there, I could do the same thing with the preset and tie everything high instantly. So those asynchronous inputs and outputs basically set those up. So let me just kind of go back to our book here that I'm following here, and they get into more details on the JK. They talk a little bit about the 74 dual JK flip-flop right there. Now, this one here is the Sept. I'm going to redo this circuit. This time I'm going to do the same circuit with the 74-112. And the reason I want to use the 74-112 is because I'm lazy and I don't want to put an inverter between each of the clocks. I'm going to change this to toggle on the trailing edge of the clock. I could go back to the circuit here. Right here. And I could put an inverter on each of these clocks, or I could just go ahead and redo the circuit and use the 74-112. So I'm just going to go ahead and close this project out and do a new project. Close project. All right. I'm going to do a new project. New project wizard. And I'm going to just put a 2 there. JK counter 2. And hit my finish. And this gives me a warning saying, do I want to create? So I created a directory. I'm going to do the same basic project again. This time I'm going to use a trailing edge clock, and something is going to change here, and we'll talk about that here. And it's a 74-112 right there. Now notice here that what comes up looks like this, so it's a little bit harder to draw this. But we're going to go ahead and use this here. And I'm going to put 2 of those in. Right there. And notice that we've got, again, we're going to tie everything to VCC other than we've got 1 clock here and 2 clocks here. So we're going to take our Q output here and we're going to bring it back to our clock here. So the drawing is a little bit more complicated because I'm using the chip, but this is typically the way that we have to do some of these things. So let's go ahead and put in my 1 input. My clock. Right there. And this clock is actually going to go into the first clock one right there. Right there. So there's my first clock one. My second clock is going to come out of my Q here. Right there. My clock here is going to come out of my second Q. so the drawing gets a little uglier there, right? Same thing, my first Q comes down here and feeds my second clock. Right there. So I've set up, I've connected all my clocks. You know, the first one comes from my outside world clock. My second one comes from my first Q. My third one comes from my second Q, and my fourth one comes from my third Q. Right there. We're going to tie everything to VCC that we want to. So I'm just going to put one VCC here at the top, and I don't know why I put it so far up. Right there. And we're going to tie why did I do it? I keep doing that. Right there. And we're going to tie everything to VCC here that our JKs all get tied to VCC. Our clear gets tied to VCC. This preset gets tied to VCC. Right there. Uh-oh. That's what you don't want to do. This is where not having a real mouse pad becomes kind of a pain in the neck. You got to be careful not to accidentally stop on one of those lines, or otherwise you connect everything up. Okay, I think everything's connected here. Oh. Okay. Right there. Okay. It looks like now we need to do our outputs. Now our outputs are going to be ugly. The way our outputs are going to be. Actually, what makes them ugly is bringing them out. But let's go ahead and put our outputs out there. And we're going to do the same thing there. Output. And we want 4 of them. I'm going to just put them right here. Let's make it a little larger to where all right. So Q2 here actually is going to come out. You know, I'm going to separate these out here. This is actually going to go to Q3. You know what I'm going to do? Move these down a little bit here. We're going to have to cross them here a little bit here. This is Q3 is going to go to here. Q4 actually goes over here to Q2, right there. This one is going to go to Q2 on the first one. this one is got to go. Oh, that's going to be, yeah, you know what? I was never hired to be a draftsman, so. That's an ugly drawing, right? But everything's connected, right, I think. That is one ugly drawing. That there. Okay. Let's just kind of go through here, and let's name the pins real quick. Q3, Q2, Q1, Q0. And we will check to make sure everything's right here. Clock. Be okay. All right. All right. Let's just go through the connections here, make sure everything's right, and then we'll look at our circuit here when it's all said and done. All right. Our clock goes into our first flip-flop clock, and it's an inverting clock. Our JK, and JK are all tied VCC, so they should toggle on the trailing clock edge each time. Right there. Our clears and presets are all tied to VCC, so they're going to not be in function. They won't do anything. Our presets and our clears, right there. Our outputs are tied. Q3 is tied to our fourth flip-flop, which is the second flip-flop in our chip, in our second chip. Our Q2 is tied to the first flip-flop in our second chip. Q1 is tied to the second flip-flop of our first chip. And Q0 is tied to the first flip-flop of our second chip. Right there. So essentially the circuit we're drawing here, and I'm drawing it in an ugly fashion, is we've got 4 flip-flops. And why is my pen? Okay. My pen is not doing anything. And I know my Bluetooth is connected because my mouse is working. Okay, now we won't. It worked 10 minutes ago, right? My pen? Not there? It's not working at all now. Now it works. Okay, you got me there. We got 4 flip-flops that there. And we're taking the only difference is we're using the bubble. Everything else is connected exactly like the first one, right? Everything is connected exactly like the first one. But what should we expect? Here's our clock. Right there. And we won't carry it all the way through, but we're going to toggle at these points in time right here on the trailing clock edges, right there. That's where we toggled it. Last time we toggled on the leading clock edges. Now, let's look at Q0 right there. Now, Q0 is going to toggle, starts out at 0, and it's going to go high here. It's going to go low here, high here, low here, high here, low here, high here, low here, and back to high there. That's what we should see on Q0 right there. Q1 toggles on these trailing clock edges. Right? So it's going to toggle here, 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 right there. Q2 is going to trigger here and here. Q3 we haven't got to. If we look at this, this is the number 0, this is the number 1, this is the number 2, this is number 3, this is number 4. Now we're going to count up. The only thing, you know, when I did using the non-inverting clock, it was a down counter. The only change I've done in the circuit is I've changed from a leading edge clock to a falling edge clock. And now I would expect this thing to count from 0 to F and back to 0, right there. Does it work? Well, we don't know. We haven't simulated it yet. And hopefully I don't have to fight with the the bit order again. Right there. I just make it plenty of time here. Right there. Enter our pins. All right, as I recall, I've got to reverse these. Group. We don't care what it's called. Bit order, most significant bit on top, that's fine. Up there. I'm going to put it that right there, but again, it's fine. We need to put a clock in. Just use 50. Right there. There's our clock. Save it. Simulate it. And it did the same screwy thing it did last time. I'm not going to fight with it again. Because all I did is I just did it 2 or 3 times, and I kept doing it the same way and still did it. We're going to ignore these numbers. We're just going to look at the data right here. And we're just going to look at the bits. The most significant bit is on the bottom. Least significant bit's on top. This is 0, 0, 0, 0. So that's 0 right there at that point. Right there. Matter of fact, let me it's the wrong thing here. Okay. If we look at this right here, this is 0, 0, 0, right? This is our most significant bit, least significant bit, right? We go here after this clock edge right here. This is 0, 0, 0, 1, right? Ignore the number on top. They're backwards. We go to this one here. This is 0, 0, 1, 0. Right there. We go to the next one. It's 0, 0, 1, 1. 0, 1, 1. Right there. So we can keep going down here. This one here is 0, 1, 0, 0, 0, 1, 0, 0. So it's counting 0, 1, 2, 3, 4. We can go all the way down through here, and we get to the point here, and I don't carry it far enough here. Right here, see there's 7, here's 8, 9, 10, 1, 0, 1, 0, that's 10, 1, 1011, 11, 1101 is 13, and then 1101 there. You can see that it's counting up. It's doing what it's supposed to do, despite the fact that I got the bid order wrong. Because if we carry this on to the next page, right here, we can see that we go from all ones here. You can see right here. 111 here. See, we're all F here, and then our next one is 0. It resets back completely. So now we can do a very easy up-down asynchronous counters with just 4 flip-flops right there. Very straightforward, very simple right there. Oh, okay, that's enough on counters for today. I'm going to change topics a little bit, and I'm not going to go deep into it. My normal 75-minute rule says that I should be only talking about another 10 minutes anyway, so. But there, I may go a little bit longer today, but that's all right. I want to introduce a completely new subject. Get there. And our new subject okay. It gives me the time in San Diego. All right, that's good to know. Okay. When we look at something called a finite state machine. A finite state machine means that you have certain states that you want to go into and say for certain conditions are met, and then certain ones up there. Let's use the case of an elevator right there. An elevator has 2 buttons and it has 3 states right there. And our 3 states is floor ground, floor 1, floor 2 right there. Those are our 3 states. If you're on the ground floor and you hit the up button, you want to go there. If you hit the down button, you stay there because you're already at the ground floor. If you're in the first floor, you hit the up button, you go here. If you hit the down button, you go there. If you're in the second floor, you hit the up button, you stay there. If you hit the down button, you go here. Now, in our elevator, there's no path between here and there unless the cable breaks. That there. In other words, we're assuming we can't go from floor 2 to floor ground without going through the first floor. That there. So we're going to assume that that's a very simple elevator right there. That's one example of a finite state machine, a very simple one. That there. So what we're going to be looking at here is we're going to be looking at designing finite state machines using flip-flops. Another example of a finite state machine we just did. 0, 1, 2, 3, 4, 5, 6, 7. A counter is a finite state machine. Now, in the case of a counter, there's a 3-bit up counter that recycles. There are no inputs. The only input is a clock. Now, an ideal finite state machine will change states only on leading clock edges. So we're in one state, we go to a next state right there. So when we look at designing finite state machines, you can do what's called a bubble graph, or you can use a state next state table right there. So we look at finite state machines. Let me look at a finite state machine that the young ladies might be more familiar than the gentlemen, a standard washing machine, right? So, you know, a standard washing machine has, we'll say, 5 states. That's there. Now, one of the states might be is idle. So if we look at a washing machine, let's just list the states that a washing machine can have. Idle. I'm just going to call it ID. You know, the idle state means that the machine is sitting there turned on, but it's not washing clothes, it's not doing anything, it's just waiting for you to hit a button, right? The next state might be fill, and I'm going to call it fill 1. It's going to fill up with water, right there. The next state might be wash. It's going to sit there and agitate during the wash cycle. The next state might be drain 1. It's going to drain the wash machine at the end of the wash cycle. Now it's going to stay in the wash cycle for so many clock cycles, or so long. We'll deal with that later on. Is that there? The next one after drain is we're going to do a rinse cycle, right there. And I'm going to say my washing machine has 2 rinse cycles. So then before we rinse, we got to put more water back in there, right? We got to fill it back up with water. Then we can rinse, right there. And then we're going to drain it again, and then we're going to do the spin cycle right there. And once we're done with the spin cycle, we go back to our idle cycle. So we have this whole concept of finite state machines. Now, this gets a little bit more complicated when we start looking at our washing machine. In the fact that in our washing machine, we have to have multiple inputs and outputs. I've used washing machines as actually final projects for an advanced digital course, so it's not a trivial project when we look at the overall full project. But for an example of how a finite state machine works, it's a good discussion point right there. But you're going to need to have inputs right there. And our inputs are listed as, I'm just going to list them, as a start button, right? You got to start the washing machine. You probably have a door sensor. I don't know. Or you may not have a door sensor. You may have a door lock. That may be one of your outputs. Most American washing machines, and I'll be honest, I know American washing machines because I've lived by myself in the U.S. and I've had to do my own clothes. Since I moved to the U.S., I haven't used our washing machine. So I don't know if it's got a door lock on it or not. That's there. I've never used it. That's there. So, as a matter of fact, I don't think my wife's let me touch it. We bought a really high-end washing machine, and I'm not allowed to play with it. That's there. But we'll say that there. It also has, for example, a full sensor. Right there. The washing machine fills up with water. It has to know whether or not it's got enough water, right? If you had a very tightly regulated water flow or water pressure, you could probably say fill for 20 seconds, but that doesn't work in most places. It doesn't work in the U.S. It definitely doesn't work in Malaysia because one day I've got 25 pounds of pressure. The next day I got 60 pounds of pressure. And some days I got 3 pounds of pressure. It depends on whether or not there's water left there. So you also need to know when it's empty. Sensor, right there. So you need to know when it's empty, right there. And then you probably also need to have some type of timer, right there. There. Now, in this class, we're not going to design, but we're going to go over the concepts of finite state machines. To be real honest, I would not design finite machines too often using the techniques in this textbook. But I'm going to get into a little bit of VHDL next week. Now, we only meet one time next week, as I understand, correct? Next Tuesday. Next Thursday, we're all going to be going for prayers and eating big meals up there. So, but regardless, I'm going to introduce a language called VHDL, which is what I use to design finite state machines. That there, when you get to whichever country, I keep confusing. I think everyone said Australia, but some people told me New Zealand. That there. So when you get there, they may use another language called Verilog. That there. It doesn't matter. That's usually the way I design finite state machines. But what you have to look at is the state transition. You're in the idle mode, ID, and you stay there as long as start is equal to 0, right there. As soon as start goes high, you go to fill 1. you stay there until full is equal to 1. Full equals 1. Then you go into wash. You stay in wash until the timer equals 0, timer t equals 1. I'm just going to call it t. So you come up with this state transition type drawing right there. Another type of finite state machine you see every day is red, yellow, green. Red, yellow, green. A stoplight is a very common type of finite state machine. You start off north-south is green, then you go to north-south is yellow, then you go to north-south is red, depending on some places. Some places don't have a north-south red cycle. Then you go to east-west is green, east-west yellow, east-west red, and then back to here. You just cycle. This is green, then this goes off, this turns on, then while that's on, this is on, then maybe some places you have both red lights on for a short period, then this one goes green, this one turns off, then this one turns on, this turns off, then this one turns on, and then we repeat the cycle. So we go from one state to the next, right there. And these are done with typical digital systems, right there. We have a way of doing that. And I'm a huge fan of finite state machines, to be honest, because probably 90% of all embedded applications are some form of a finite state machine. I don't care whether you're controlling a wash machine, a dishwasher, a microwave oven, a stoplight, a pet food dispenser, a heating and air conditioning system. I don't care what it is. If you're using a microprocessor or digital electronics to do it, you're using some form of finite state machine. Even the microprocessor itself is a finite state machine. So finite state machines are used in every type of control application right there. So they're very, very important, and we're going to spend a little bit of time looking at them there. And counters are just a special case of a finite state machine. That's there. So with that said, we'll come back to that in a lot more detail. I just wanted to throw this topic out today. And we'll come back to counters, but using the approach of finite state machines for counters right there. So how my time is, see, my prediction,